So let's start. So it is a great pleasure to introduce today's speaker of our Albanova colloquium. Welcome everyone to the talk Topology and Chirality by Claudia Felser. I will give a brief introduction because Claudia doesn't need introduction. She is one of the most famous condensed matter physicists now, with very many impactful work that most of us know, like in particular recently the discovery of magnetic wire semimetals, that was a big resonance, and many other things. Probably would be I couldn't fit everything in a short introduction, and let me just give the brief bio sketch. So Claudia got her PhD at the University of Köln in 1994, and habilitation at the University of Mainz later. And she was working as assistant and associate professor and then full professor in Mainz up until 2014. And since 2012, 2011, she works as the director of Max Planck Institute of Chemical Physics and Solids in Dresden, and it is one of the most important research institution in Europe, with a true leadership in true world scale leadership. And her leadership, this institution achieved many breakthroughs in design of various materials, multifunctional materials, design guided by theory, by electronic structure calculations, and discovery of design of new materials for various kind of applications, and including applications for quantum technology and for energy, as well as spintronics, thermoelectric materials, solar cells, quantum materials, topological materials, skyrmions, materials with skyrmions with potential for data storage, and superconductors. So, and I will not take much time out of her talk, so I will now pass the stage to her, and thank you very much for being with us today and this exciting and interesting talk.
Thank you, Ega, very much for the invitation. I have to thank the organization and the University of Stockholm to invite me to this very famous lecture series, and I'm happy to contribute. And thank you also for the very kind introduction. And I not there in person. Anyway, I was in Stockholm recently. I like the city, and I hope I can come soon back and talk to people in person. So I want to talk a little bit about topology, and chirality and the connection. So because this is just now what connects excite me mostly. Before it was topology and magnetism, but now I'm also inspired by the concept of chirality in general. And I think there are so many open questions, so that we think we can spend the next 10 years only on the subject. And we think there's only the tip of the iceberg, which is known. And since I'm always was very interested in interdisciplinary science, so like Igor, so he likes to bridge everything. I want to bridge even today my talk from high energy physics to chemistry, because I think there are many connections and open questions, and maybe we can learn all together some new stuff. And I would say I don't know everything, so if you have some comments, even if I ask questions, because I think there are more open questions than resolved questions, I would happy to listen. So what the dream of a physicist is, you have a Hamiltonian, And so the theoretician like Igor, they write on the Hamiltonian and they ask us, the experimentalists, please prove what is the Hamiltonian true? Do you have materials where you can really see properties of such a Hamiltonian? And this is what we do. So our expertise is really in growing high quality single crystals, and then we love to do investigations there, and we use external forces here, like temperature, magnetic field, electric field, pressure, and twist. And so we would like to see proof experiments which may be related to the universe. So we still want to do this horizon experiment, which some theoretician has proposed, and so on. But we know also what we see is simply like a simulation, or we see the quasi-particles, which can give us some information, or at least some information about the Hamiltonian. So today my talk is about chirality, and I think chirality in two directions. So the chirality in real space and chirality in reciprocal space. Here you see electrons where the spin and momentum is locked, and for this reason they are also chiral. And I still have the dream that we can make some connection between chirality in real space and reciprocal space, which means we could maybe make a connection or try to have a better understanding between chiral quasi-particles and maybe interesting materials in real space like molecules, crystals, etc. And topology is a concept which is very much connected to the chirality of the electrons, because spin and momentum locking is very important there. And the basis of topology comes from mathematics, and we have objects here, and it deals with the surface of objects, so it's very deep in mathematics. So that here this object has has the same surface like the Earth, for example, a ball, or it's different, but it's distinguished from a donut where we have a hole. So this has the same topology like a coffee pot, where we have a hole here in the coffee pot. So we can describe it by simple equations, and we can then continue with a number of holes and so on. And so these two different topologies, they are distinguished. Here we need, for example, a knife to cut the donut, and if we cut the donut, it goes into the topology of a pancake. So there have to be very radical methods to change the topology. And this concept was now turned into a concept for condensed matter physics, but it's also available beyond mathematics in many other fields, including chemistry. So it has led even to this fantastic Nobel Prize, which is related here to this paper of Haldane, where he predicted that the quantum Hall effect can be found without Landau level in a system where we have an intrinsic magnetic field. And this has inspired, this was work which was already done in 1880, but it has inspired Kane and Mehle to say, okay, we can have also quantum Hall effect. If we have spin-orbit coupling, then we have a so-called quantum spin-Hall effect, while Haldane spoke about the quantum anomalous Hall effect. I will later explain what does it mean in graphene. Graphene, so if you need spin-orbit coupling, you need heavy elements. So graphene is maybe not the ideal material, but with this publication, immediately people recognize that this can go far beyond what the quantum Hall effect was. This was a complex system in two-dimensional electron gas, where you did some measurements at very low temperature and ultra high fields, but it was not an area of research broadly. But here, the quantum spin Hall effect and the topological insulators has opened a huge field, also concerning materials. And I will tell you, this is not surprising, because we have overseen the role of topology in material science for many years. And nowadays, I would even call it's relativistic material science. It has a big influence. It might explain old properties, which you already know since a long time, and I still have some interesting things in my mind, but it also can predict very interesting new properties, and it helps us now to use even the single crystals for as examples for investigating maybe Hamiltonians which were proposed for high energy physics or for astrophysics. But the concept is very easy, and there you maybe already recognize that topology is not a rare effect. So if we take the example of the topological insulators or semiconductors, which was the starting point. So a semiconductor and insulator has a valence band and a conduction band. So the valence band is occupied by electrons. Then there's a band gap between the conduction and the valence band, and we have the so-called Fermi energy, which separate occupied from unoccupied states in between. And the band gap, the size of the band gap scales very often with the bonding strength between the atoms, because it shows us something between bonding and anti-bonding states. So if we have sodium chloride, we have ionic crystals, we have a large band gap. Therefore, sodium chloride, calcite, the salt you have on your table, is wide, while other semiconductors where the bonding is much more covalent and stronger, so they have a small band gap. And what can happen is also that the band gap becomes even negative, so we have an overlap between the conduction and the valence band, and this is if the bonding is very weak, and also if the elements become heavier, they are bigger, so the bonding becomes less strong. So, and very common is this really in heavy elements, also for another reason, not only for the size of the atoms, because also if we go to heavier elements in the periodic table, so the 1s electron becomes faster, nearly speed of light. This leads to contraction of the outer s electrons, and very often this is the 6 or 5s electrons or even 4s electron of an element like indium, tin, or lead, which then goes lower in energy, so it overlaps as a conduction band, it overlaps with the valence band, and then we get these crossing points here. And depending on the symmetry, these crossing points become forbidden crossing, and especially if we have heavy elements, we have the spin is not a good quantum number, so this is very often a forbidden crossing, so it allows that this crossing is forbidden, so we open up a band gap and we get the situation like we see here. So we get a semiconductor insulator again, where now we have a part of the conduction band in the valence band and vice versa. So from the picture of topology, we symbolize this trivial insulator like a donut, and this topological insulator like a Möbius stripe. And they are topologically distinguished, so I cannot transform a donut into a Möbius stripe without using, again, a knife or a scissor. And as I said, this is quite often. So half of the elements in the periodic table have this inert pair effect, this outer s electrons which are contracted, they are lower in energy, and then the conduction band overlaps with the valence band. So it's not a rare case. So, but this has consequences, because now, in case of this topological materials, the valence band and the conduction band are connected. So we have this very strange surface state, which are protected by symmetry. So we cannot destroy the surface state because here this transformation is not possible. And at the same time, this is also related to spin. And in this electrons, the spin and the momentum is locked. So therefore, we have a very special situation in this material. So the spin, and if the spin and the momentum is locked, our electron is chiral. So it fulfills the conditions of chiral. So they behave like the mirror, like a mirror picture, very similar like what we know from the one hand and the other hand of crystals, of molecules. So this leads also to an observation that if the spin and the momentum is locked, that the electrons cannot be scattered. So they behave like on a highway. So they are not allowed because they cannot scatter into the other spin direction. And this leads to very interesting observation. I don't have the time to talk about this. Many of these compounds, the topological materials, show very high mobility. The electrons flow more like a fluid than like a gas. We see that the scatter rates are suppressed. And we might see even spin polarized currents, as what was observed recently in some topological chiral crystals. So this makes a nice connection to chemistry, which I'm also interested in. So despite of the chiral electrons, which are based on the spin momentum locking, we can have chiral molecules. I already mentioned, so in carbon containing compounds, they can if I have 4 different ligands of a carbon, so I always have a chiral center, and the DNA is chiral, but we can have also chiral crystals. And as in physics, where we are more interested in electrons, in chemistry, we are more interested in chiral crystals. And since we are interested in recent days in chiral topological material, we had some collaboration also, we have a lively collaboration with Ben List, who is interested in chiral molecules, and the meaning of chiral molecules became very clear, I think, this year, because he did chiral catalysis with small chiral molecules, which has led to the Nobel Prize for Ben List. So, but there are other concepts also, which are, again, also very similar in chemistry. So aromatic molecules, and the most popular aromatic molecule in physics nowadays is graphene. So everybody knows graphene. So graphene, all these super exciting properties of graphene are related to aromaticity. And also here, topology plays a role, because graphene is aromatic because it follows the Hückel rule. So graphene is built by benzene rings, and benzene is an aromatic molecule because it has 6 carbon atoms and 6 p electrons. So on every carbon atoms, we have 1 of these pi electrons. And if we have 4 plus n plus 2 pi electrons, the compound is aromatic, but we can have, which means the electrons are delocalized, and this is a nice thing over graphene. While if we have 8 carbon atoms, for example, we could make a ring with 8 carbon atoms and 8 pi electrons, it's anti-aromatic, so the electrons are localized. So this is also strongly related to topology, and if we make a twist in the molecule, so these rules are inverted. So now benzene kind of ring with a twist would be anti-aromatic, so the electron would be localized, while if we would have 8 electrons and 8 carbon atoms, it would be aromatic. And it's possible to make this by synthesis, so we can make these molecules, and they have different really distinguished properties simply by giving the whole crystal, the whole molecule a twist. And this again makes a very nice bridge also to twisted graphene. So here we can take this giant aromatic molecules, and we take 2 layers of this giant aromatic molecules, and this can be even chiral, so we can twist it in one direction and the other direction. So we can make a crystallographic chiral crystal here out of this. And then we can, it shows different, if we have these 2 layers which are twisted, they show very distinguished properties from graphene itself. It shows superconductivity and an insulating state. And from my viewpoint, I think this can be also interpreted by doing, by simply thinking about aromaticity, where you have here areas which are aromatic and areas which are anti-aromatic, which are localized, which are also reflected in this superconducting areas and this insulating areas. But it shows how much the thinking about topology, symmetry, and so on can still make very nice bridge between different areas of science, and can change maybe our viewpoint of scientific investigation. And here we can also think about chiral twisted graphene. Anyway, coming back to all inorganic materials. So from all the inorganic materials now, they are all characterized now, whether they are topologically interesting or not, whether they're semi-metals, whether they are metals, enforced semi-metals, white semi-metal, higher order topological materials, and even some magnetic materials were also recently investigated in this direction, whether they are topological or not. But the very surprising thing is that 25% of all the known inorganic compounds are topological, and this is quite a high number. If you thought at the beginning there were single compounds, and if you see also the fact that so between the invention of the quantum Hall effect and topology, there was such a long time. And this is for me amazing. If you could, so nobody ran accidentally in topology in between, which could have happened since topology is a quite common phenomenon. So you can go to websites and even click here on the websites. I took here hafnium telluride, for example, and I told you it's already on the lower part of the periodic table. So So if you see from all the different combination of hafnium and tellurium, you find a few which are trivial, but you find also many which are topological, and one semi-metal. You see already from this ratio that topology is not a rare concept. So what do we do? So we do first some theoretical, or we look for theoretical prediction from some theoretician, or we are involved in some theoretical prediction like high throughput. So we like to make then the synthesis of the crystals, and we wait that Igor maybe makes a nice prediction, or we are now working with his friend Maxim. He came up also with many predictions, so we make the corresponding single crystal. So we try to verify the electronic structure, and very often this is by photoemission, because resolved photoemission allows us really to compare the theoretical band structure, electronic structure, so really see whether we have this band inversion. Here we have a semi-metal, which I will explain in a minute. Then we look for some interesting properties. Sometimes we have not only topological semi-metal, so this shows also superconductivity, like here under pressure, which maybe makes this material a candidate for topological superconductivity. And our dream is maybe at the end to build qubits out of topological superconductors and quantum, for example, anomalous Hall effect. This was a proposal of Shushen Zhang. So this is what at the end is our dream. And then we go back more or less and look into more complex systems. So far, the whole concept of topology is based on a single particle picture, because then you only need some group theoretical thinking, and you can use some simple Wannier function and so on, and you can characterize this. But in the moment when electrons interact, it becomes more exciting. This was the example of the twisted graphene, where you have strongly interacting system, but then it becomes also more complicated, and our simple picture maybe is not valid any longer, but these are the next steps. So as I said, it's only the tip of the iceberg. Already we know how many materials are topological, but I still think we can be busy for many, many more years in the field of topology. And again, another example which shows nicely the concept again. So if we come to some very concrete example, for example, I didn't choose bismuth selenide like everybody. I like to choose gold, because gold is also, we are very familiar, and it has this wonderful color, and this wonderful color you can say is due to relativistic effect, or we can even say it's due to topology. So compared to what I explained already on one of the earlier slides, so compared to silver, where the 5s electrons are less contracted relative, here in gold, due to relativistic effect, it gets much stronger contracted. Therefore, the transition from 4d to 5s of the electrons is smaller, and therefore gold is not boring silver. Gold has this fantastic golden color. So can we see topology in gold? And here is the electronic structure of gold, and it's a metal, but you see it's the same effect as what I show in my drawings, that you have here this p-type band. Here is the Fermi energy, and here we have the s band, which are crossing, and here you nearly have gap situations, so the gold can be also ionized, and you can put additional electrons in compounds, so you get maybe an insulator. And indeed, here also we could show by 2-photon electron spectroscopy that the conduction band is connected to the valence band with this special surface state. The whole story should be understood in the context of the, as I mentioned before, in the context of the quantum Hall effect. So I want to remind you, this is a nice draft. So the quantum Hall effect was a two-dimensional electron gas. So you simply can think about electrons in two-dimensional, forget what is the real material. This is not so important. And if you apply a very high magnetic field and go to very low temperature, so there were edge states observed. You saw already for the topological insulators, this electrons where the spin and momentum was locked, and in this two-dimensional electrons, it was simply at the edges of the material for both spin direction and the topological insulators. So you have the crystal, and it's all over the crystal. The quantum spin Hall effect, the prediction from Kane and Mehle, so they have this whole effect without a magnetic field, because now, as we learned, the spin-orbit coupling plays the role of the magnetic field, so we don't even have to apply a magnetic field. And if we have an intrinsic magnetic field, this was a prediction of Haldane, so you suppress one of the edge states, and then you have something which is a dream of a spintronic person current at the edges, and therefore we are interested in magnetic wide semi-metals. Exactly, we want to have this situation and at room temperature, because then we can make spintronic devices. And all of this quantum effects have their simple classical counterparts, and most of our measurements, they play a role here, because most of the time the measurement of the quantum Hall effect is exactly the same as the measurement of the Hall effect. So simply to show you, you might be a theoretician, what we do is more or less we take our crystal, which you already saw, and we put it in a machine, we cool it down, we measure the transport here, and eventually we apply a magnetic field. And this is a Hall effect, and if we have magnetic materials, we have this intrinsic magnetic material, but today I focus more on the non-magnetic material. And what was surprising also for me, what recently was discovered, if you saw my slide, so zirconium telluride 5 is a very good topological material. Many interesting properties were discovered in this compound. But even if you simply look on the intrinsic properties of this compound, it was found that even in the three-dimensional crystal, not a complex two-dimensional electron gas, but the crystal is a little bit quasi two-dimensional. If you see here, you could imagine this kind of layers. You see this quantum Hall effect. So you see exactly the plateaus which Klaus von Klitzing saw when he did his measurement on the two-dimensional electron gas. And on top, even in a single crystal, nothing else in the single crystal, but a high quality single crystal, you can even see a fractional quantum Hall effect. So there's a nice connection between topology and the quantum Hall effect, which is realized here in the single crystal. Okay, but I want to talk about chirality now and make the bridge to chirality, and I start with wide semimetals, because here the chirality of the electrons plays an important role. So simply coming back and repeating it again, since this is a colloquium. So this is a picture which I partially made with Ben Hayan, but also refers to the paper I had with Prenea, who already gave a talk in this colloquium. We have the overlap between the conduction and the valence band. And depending on spin-orbit coupling, here we have this area of overlap, which is here more a line in the three-dimensional plot. And we can have the topological insulator with the surface state and the spin momentum locking of the surface state of our crystal. But what can be, depending on the symmetry, we can have degeneration, so protected by symmetry elements like rotation axis, for example, that not all the states here on this line get gapped, so we can have this Dirac or wide semimetals. And especially the wide semimetals are interesting. I will make the distinction in the next slide about Dirac or wide semimetals. So Dirac semimetals, you have this crossing point, this degenerated point at high symmetry point. So if we draw the band structure, we most of the time draw the spaghettis along high symmetry points. And so sometimes, but in wide semimetals, they appear in not high symmetry point, because wide semimetals have no inversion symmetry, or they have time reversal symmetry broken, so the symmetry is reduced from Dirac to wide. But the interesting point is now we have here 2 points in the electronic structure in wide semimetals, which shows 2 different chiral electrons. So these points are chiral. So we see this for experts also in the different sign of the Berry curvature. And this makes very interesting properties. So this Y points behave more or less like magnetic monopoles. So they are chiral, and the surface states are here connecting this Y points projection on the surface and are fermions. So because of this chirality, so this Y points and the Y fermions became more attraction, I would say, than Dirac semimetal, but more or less, if you apply magnetic field, what you do in a Hall measurement, a Dirac semimetal immediately turns into a wide semimetal, and therefore many Dirac semimetals shows the same properties. So as I said, the Dirac point, you have a fourfold degenerated point, while in vial, so you would achieve a vial out of a Dirac if you would strain. So graphene has a Dirac point, this fourfold degenerated point. If I could strain graphene, so I can turn it into a vial point, because due to the structural change, so I reduce the symmetry, and I have then this Y point. But you can do this also by making material magnetic. So every crossing point in a centrosymmetric ferromagnet is a Y crossing. So therefore, for us, it was so exciting and so easy to find many, many interesting new Y points. So why are vial semi-metals so interesting? So I said at the beginning, the physicists like to have their Hamiltonian, and then they can say, look, like, can you find a Kitaev spin liquid system? This is our Hamiltonian, think about the crystal, and so on. So, and now having vial semi-metals as a possibility, so has immediately led people like Burkhoff and so on, and Wolovic, I think he was the first, think about that there was a anomalous non-conservation law, the so-called chiral anomaly, which was formulated for the vacuum state, or the asymmetry between particles and antiparticles for the vacuum dispersion here. And this equation can be transferred. As I said, we like to see look for quasi-particles, so electrons and holes here, which would have the same asymmetry because of the linear dispersion and the degeneration point we have here too. So which follow exactly this. And I was very proud that even in Wikipedia, you already find the important information about this chiral asymmetry or this paritational broken parity about this. So here, this was for sure for other people in topology, something which was exciting, that the theoretician again have predicted something, and then suddenly again it's a quasi-particle. It was so it's this is my symbol to describe quasi-particles, not the chicken, the real chicken. So we see this in transport of electrons, what was predicted originally for high energy physics and particles and antiparticles. Okay, so there was a long list of predictions then, and so what we do normally is like we go to the archive in the morning and we look what the theoretical physicists predict. Then we look, some of them maybe already predict the material, some simply a concept, and then we look how we can realize this. And here for vial semi-metals, there was this prediction, this based on this chiral electrons, that we can see the Fermi arcs. I already explained this. We can see the chiral anomaly. So if we, and the idea is here, if we do an experiment where the magnetic field and the electric field is in parallel, we get the asymmetry between the two Y points here, and this should be reflected in a negative magnetoresistance effect. So vial semi-metals, which are non-magnetic, show very similar properties like a magnetic system, because we can make here the asymmetry between the electrons of one spin direction and the electrons of the other spin direction. There was another prediction from from Subesachev and other people in astrophysics that this could be also, if you apply additionally a temperature gradient, that you can find a situation which you have in case of the axial gravitational anomaly, and here you get the asymmetry because of the temperature gradient. And in general, based on the Berry curvature, so here the Berry curvature plays an important role in, this is a geometric phase which you have if you go around the wave function in a closed loop. And this is super important in this topological material, and we can get a lot of information out of there. And people recognize the importance of Berry phase before they recognize maybe the connection to topology, especially for some anomalous Hall effect and anomalous Nernst effect. So we see very giant responses, and this is why I think I do so many things. But these giant responses might lead to a new concept of thermoelectric materials. So it's not like totally disconnected. All the things are very much connected. And it's amazing how the concept of topology has changed the thinking about materials and how it helps us nicely connect suddenly high energy physics, astrophysics, but also maybe application beyond of quantum application. So the materials, the first material, which was predicted by Andre Bernevik's group and probably Hassan's group at the same time. So this was simply also a success because there were predictions before, but this material was easy to grow. It's a very simple crystal structure. It's a non-centrosymmetric compound. If you do a calculation, here's a reciprocal space, you find many Y points which are quite close together, which is quite often. So in non-magnetic materials, these Y points are very close together. In magnetic materials, they are a little bit far away. So, but then we also were able to grow all the single crystals, a whole series of compound. And you see here the Ingere soft photo emission. So you see really that you have bands which are nearly crossing at the Fermi energy. And if you increase spin orbit coupling, which means you make the material heavier, so niobium is lighter than tantalum, you see that you have a spin orbit splitting here. So the bands are more splitted. But also the distance between the Y points become larger. So you can then, the first proof is also, can we see this Fermi arcs? This was the first experiment all the groups did. And we did this also for all the 3 compounds we have grown. And this is a density functional calculation. And this is as an experimental measurement. And you see that you have quite a good agreement. So the next experiment I told you was that this is the way we have grown the crystals. This was by chemical vapor deposition. Therefore, we really could grow this very nice big crystal. But here you see this giant responses. So you see here the resistance versus temperature. And you see if we have no magnetic field, we have here wiggles. And these are not noise. These are quantum oscillation. It allows us to say exactly where the Fermi energy in our crystal is, so we know exactly how close in our crystals we are to the Y points. And you see at 0 magnetic field, it looks more like metal, the material, but in the moment when we apply a magnetic field, and this is very typical for all the semi-metals, Dirac and Y, so we get a big change over orders of magnitude in the resistance. So the magnetoresistance is like millions. You might remember there was spintronics and there were magnetoresistance in 100% also. And this has drawn attention because you could make retards out of this, but here this effect is much larger. And if you see the upper curves in the magnetic field, it behaves more like what we would say here, like a semiconductor, but then we would expect it goes up and up and up. And it's also very typical for all these materials that we have the plateau here, which we think is assigned to the surface state, which are there in this material in the magnetic field. So then Johannes, he wanted to go beyond the experiment which were predicted. So he wanted to really do the chiral anomaly and the gravitational anomaly. But for this reason, we have to make sure that our measurements are reliable. So you need a very asymmetric crystal. So we have fibbed micron ribbon of niobium phosphide here, which accidentally doped the crystal a little bit with gallium, but this was very good. So we saw again this quantum oscillation, which allowed us to just say where is the Fermi energy relative to the Y points, and the small doping made the crystal even better because now we really had the situation that we were very close to the Y point. So in transport, we really have to have the Fermi energy close to what we want to measure. Otherwise, we see not directly the effect. And what we did a normal Hall measurement where the magnetic field is perpendicular to the current, and we saw a positive magnetoresistance effect. And then we switched the magnetic field, and then we saw really up to room temperatures a negative magnetoresistance effect in this compound. So this was already good because this has shown that our micron ribbon shows the expected properties. And this then has motivated us to do the second experiment, the prediction from Subier Sachdev and Karl Landsteiner and others, the gravitational anomaly, and so we applied on top a thermal gradient, and this is quite challenged in this small with this nanoribbons on top of low temperature. But here you can see the prediction exactly from Landsteiner and from Zubier was that this should be a B square behavior at low field, and then if you change the if you go to higher field, it changes the direction and should go versus zero, the thermal conductivity. Here we have conductivity simply as for having the comparison. So nowadays, so to other materials has shown this chiral anomaly. This was the gadolinium platinum bismuth done here in our lab, and bismuth itself is slightly doped with antimony from measured by the Ohio State University. So this made it up to the New York Times and motivated us to look for more exotic things. And the other thing was like which was the axion. So the axion, there was a prediction that we can find axion insulators in this material, and one prediction was based on a work of Shushen Zhang, with whom I worked since the beginning of topology, I have to say. So Shushen brought me in topology, so I was very thankful to that he spent so much time with me explaining from somebody who knows to make materials, and I like to have did it mostly for spintronics. So he turned me into topology, and he had a paper that you can find axion as it's a particle which was predicted to explain dark matter and the violation CP symmetry violation and quantum chromodynamics. That, oh sorry, it's in German. Sorry, because this was for a German talk. So anyway, you find it in Wikipedia if you want to have, sorry, I copied the German slide. Anyway, so the starting point was that we looked for chiral crystals, and this is a chiral crystal, by the way, and for new fermions, and tantalum selenium iodide was a candidate material. So we did the band structure calculation, and we thought, wow, this has such a nice band structure. So it's an ideal vial, because we have quite a big gap here, and the only bands which are crossing are the bands which lead to the vial crossing. Okay, so this was super exciting for us. And then we looked, we measured the transport, and then we were disappointed because the material is insulating, and the vial semi-metal should be semi-metallic. We expected a property like in tantalum phosphide and so on. And looking into the APES data, it shows really, so you have this linear dispersion in this compound, but you have a small gap around the Fermi energy. And then we looked in the literature, and this is because we have a charge density wave. But then we recognized that in this paper here in 2013, so Shushen already predicted a chiral anomaly, charge density wave, and axion strings from vial semi-metals. So learning from this, we recognized also that if you have this situation, you might can slide the charge density wave, so get rid of it to get back to the vial physics. And this is drawn here in the sketch. So because of the charge density wave, we open up a band gap, so we lift the degeneration. But if we could bring it back, we could see the axion, so the axion related to the charge density wave Fasan. And this was exactly done here in this experiment. And you see again, the E dot B term is very important. So we have to measure the magnetic field perpendicular to the current. We don't see anything. And if we measure the magnetic field parallel to the current, we see that we can have a negative magnetoresistance effect like we have in a vial semi-metal. So we are now looking for light matter interaction, also experiments in this direction, and so on, to have further proof of the axion Fasan in this material. But we have also ideas about other materials where we can find similar effects. Sorry. Yeah, and very important was also, so the prediction was also that the distance, the charge density wave should scale with the nesting vector between the y points. And this is exactly what was found then in synchrotron-based XRD. So we have the super reflection peaks about the main reflection, which is related exactly with the vector between the two axions. Okay, so meanwhile, also in magnetic materials, like this manganese bismuth selenide in monolayers, so which is a magnetic topological insulator. So this axion behavior was found So as with a different concept, so you depends on the magnetization of the two layers in this materials, whether you have a topological insulator or an axion insulator. So with the last slide, I want to come to new fermions. So despite of having chiral electrons, we can combine chirality in the crystal structure and chiral fermions. And this was done, the prediction in this paper. So you can go maybe beyond the 4-fold degeneration by going to 6-fold degeneration or 8-fold degeneration. But in a chiral crystal, we can have also this degenerated point of this Y fermions at different energies. And in this article, we already predicted series of materials, and the B20 compounds are especially interesting because they are crystallographic chiral. And this has led to a nice conclusion from the referees of our paper, so which I like. He cited Heisenberg, that if you even have this new fermions go beyond what you can have in the universe, because if you put a lattice on the universe, you might find something crazy, totally new. And I hope this inspires also more theoreticians to go beyond what they know from high energy physics and astrophysics, maybe to think about further interesting fermions in topological materials. So if you combine chirality by itself is already interesting in inorganic chemistry, because you can see in physics, so you can have optical activity. So for nonlinear optics, people look for chiral crystals. And here it's again interesting, what most of the people don't know, that 20% of all inorganic crystals are chiral. So chirality is also topology, 25%, chirality, 20%. So these are not very rare things, so properties. So it's surprising that people didn't see things before. So if you compare normal Y semimetals with these chiral new fermions, so we have now the Y points at different energies, so which gives us a bigger range of energy where we can play around with properties. And we have Fermi arcs which go all over the Bryan zone, so they are connecting one Bryan zone to the other. So, and if we have two enantiomers, they are chiral, they behave like not only in the crystal structure, the crystal behaves like its mirror image, it's also in the electronic structure. But it's not in the band structure, because the band structure is like in chiral molecules, molecular orbitals are the same, but the wave function is different and the Berry curvature is different. So we are looking always for handles on these chiral things, and you see that they behave differently, and therefore my Y points have different color because they simply have different phase. So in the real system, here in the B20 structure, we have a 6-fold degenerated point. So we have 2 points here, 6-fold and a 4-fold degenerated point. And at the gamma point, we have a 4-fold degenerated point. At the R point, we have a 6-fold degenerated point. You see there are different energies. They even have different degeneration, but they are also a pair. So, and here you see what happens if you apply spin-orbit coupling, you get the splitting, and spin-orbit coupling therefore plays also a role. So luckily, in this case of materials B20, we could, in one case, we could grow crystals of different chiralities. This is still an open question, how to grow one-handedness and the other-handedness, because energetically they're exactly the same. They have the same atoms. So there are some proposals with seed crystals. We tried, it doesn't work as nicely. So we have more the feeling it's more statistically. Anyway, so we are able to grow at least handedness-free crystals here, which you can also see in the XRD. And then you do what you do, you look for your photos. Here we see the 4-fold degenerated fermions, and here we see the 6-fold degenerated fermions in Engelreshoff photo emission. And you see a nice agreement between the, then here always, this is the calculation, the photo emission calculation, photo emission calculation, photo emission. You see very nice agreement. We can make both enantiomers. They look in the band structure exactly the same. But if you look very careful on the surface, because the band structure for both enantiomers is exactly the same. As I said, the phase is different, so they have different phase. So the electrons are also chiral here. So this we see then this is sometimes you need a little bit guidance for the eyes, but we have the chirality of the surface state in these two enantiomers, which you nicely can see. These are simply dots which get color, but we cannot really see it. But I will show you in a few slides that we also, if we use circular polarized light for the photoemission, we can see the chirality. So what was also here interesting, because this compounds have higher Chern numbers, this is more for the experts in chirality. And this was exactly what we could show here, because we had this platinum, no, this was also palladium, gallium, so we could show the splitting in these crystals here, which was a proof then that this is a Chern number for the in case of the surface. Okay, so we did also STM investigation, and it's a little bit surprising since there is only a difference in the phase, but even in the quantum interference, you see nicely that the enantiomorphs have different chirality here in the pattern of the STM, because there is an interaction between the surface state and the bulk, which allows and is strong enough to see that we have a chirality here. So similar work was done also on other single crystals. We did some collaboration with Hassan, who was interested in cobalt silicide and rhodium silicide. We have now films of rhodium silicide also, which is very good if you want to continue to do more device kind of investigation here. And they all have very nice quantum oscillation, not all, but some of them are of our crystals are of high quality, so that we really get nice quantum oscillation. And the quantum oscillation tells us exactly how good our agreement is between the calculation and the experimental measurement from a different perspective. And we just recently did more on the quantum oscillation together with Philip Moll, and we find very, very interesting effect going beyond the simple interpretation of the Fermi surface. So, but what I said is simply how can we prove the difference here? And this is related to the Berry curvature. So if we look for the Berry curvature for the both enantiomers, you see this change the sign. We don't have overall Berry curvature, which is very large because we don't have so many symmetry elements, because we want to have chirality. But you see the sign, the local Berry curvature is very distinguished. And I think there was very nice work also from Angel Rubio and others. They talk about the local Berry phase. And so this can be maybe shown in circular polarized photoemission. And we did here first measurement in collaboration. And you see also here is the Fermi surface here's a simple Fermi surface with Ingerois photoemission compared to the calculation. Again, very nice agreement. And then if you color it by doing the circular polarized light, you see nicely that the enantiomers behave. It's again like the mirror picture. So we see a difference in two enantiomers by the orbital angular momentum. We can do catalysis with this, and I have really to come to the end now to I think these are very good catalysts. So it shows you we can also here bridge very nicely. We tried first hydrogen evolution reaction, and here is the platinum nanoparticles. You see some of the chiral crystals behave even better than the conventional platinum, because we think it's related also that we have a big area where we can play around, and we think here we can go now a little bit more in direction of chemistry. So I hope I have given you a little bit an impression that chirality in the electronic structure, chiral electrons where spin and momentum lock, is very exciting, and it might be showing up in more interesting properties because 25% of all the inorganic compounds are topological. So we are hoping that more physicists like Igor comes up with proposals and Maxim and others. And we think that chiral new fermions are very interesting, and we think there's still a lot to investigate, light matter interaction, and maybe there's more chirality hidden so far in this chiral new fermions and other properties. So people showed recently that you can have a long spin polarized current over micron meters in chiral topological materials. So this would help very much for spintronics. So, and yeah, I think there's a lot to do. So my outlook is, I hope soon we can see more axial and chiral anomaly and maybe combine chirality with magnetism, etc., and can do more interaction of interesting interaction between molecules and maybe chiral surfaces. With this, I thank you for your attention, and I'm very thankful to my fantastic collaborations, especially the young members, my young collaborators like Johannes Goeth, Niels Görl, Schröter in photo emission, Johannes in transport, and Maya on the theory side. Thank you very much.
Thank you very much, Claudia, for this beautiful talk and so many great results and so many things happening. And let's thank Claudia. I think we again in Zoom era we probably cannot upload like we usually do in 3D and Panova Colloquium. So, but there are now messages